Scout is a solid rocket motor launch vehicle developed by NASA Langley Research Center as a cost-effective vehicle for use in a wide variety of space research and application projects. Although it is the smallest vehicle in the United States inventory demonstrating orbital capability, Scout has proven its versatility and performance over many years of service and has achieved a reliability record unmatched by any other launch vehicle in the world. The purpose of this film is to acquaint you with the technical aspects of the Scout vehicle, its systems and performance capabilities. Scout mission capabilities include launch of Earth orbit satellites, deep space probes, and atmosphere re-entry payloads. 3 permanent launch sites are utilized in the Scout program. The site at Vandenberg Air Force Base, California, provides launch azimuths from due west through south, but is used principally for polar orbit and sun-synchronous missions launched in a southerly direction. The launch site at Wallops Flight Center, Virginia, offers an easterly launch azimuth and is used for missions with orbits inclined to the equator. The San Marco launch site off the coast of Kenya, Africa, provides near-equatorial orbital launches for Scout vehicles. Space probe or re-entry missions can be launched from any of these sites, but are usually accomplished from the Wallops Flight Center. The United States launch sites include clean room facilities for spacecraft buildup and checkout, and facilities for dynamic spin balancing of the spacecraft and fourth stage assembly. The San Marco range has limited clean room facilities, but no spin balancing capability. Orbital capabilities of Scout extend from near-Earth circular orbits in the 500 to 1,000 kilometer range to highly elliptical orbits with apogees beyond 100,000 kilometers. Nominal payload weight capabilities for a 550-kilometer circular orbit range from 143 to 194 kilograms. For an 1,100-kilometer orbit, nominal payload weight capabilities range from 97 to 135 kilograms. Precise payload weight capabilities vary depending on the launch site and mission parameters. Scout performance capabilities have been continuously improved throughout its history, and future improvements could further increase these current figures. Scout stands 23 meters tall and weighs approximately 21,000 kilograms exclusive of the payload. Its basic configuration comprises 4 rocket motor stages and 5 transition sections, plus a heat shield. Alternate versions of some of these major components, plus additional options, offer a variety of final configurations available to suit specific mission purposes. The first stage motor is the Algol 3A, which develops an average thrust of approximately 109,000 pounds. The second stage motor is the Castor 2A, which develops a thrust of over 64,000 pounds. The third stage motor is the Antares 2B, developing a thrust of approximately 28,000 pounds. The vehicle fourth stage is the Altair 3A motor, which produces a thrust of over 5,700 pounds. Ignition of each of the Scout motors is accomplished by dual squib actuated rocket motor igniters, which are inserted in the forward end of the propellant core when the vehicle is assembled. The transition sections of the Scout vehicle structure are designated as the base A, B, C, D, and E sections. These serve the dual purpose of connecting the vehicle stages and housing systems components essential for vehicle stage ignition, guidance, attitude control, tracking, telemetry, and destruct functions. Fourth stage timed command and telemetry monitoring are provided by components attached to a module around the fourth stage motor. Wiring essential to electrically interconnect the transition sections is routed through the external tunnels attached to the surface of the vehicle. The spacecraft is mated to the vehicle on the E section. An optional fifth stage is available for Scout. In this configuration, an F section joins the fourth and fifth stages, and a G section is the adapter from fifth stage to the spacecraft. The fifth stage is the Alcyone 1A motor, developing a thrust of 6,100 pounds. Since this configuration is rarely used, it will not be detailed further in this film. A heat shield encloses the payload compartment to provide aerodynamic efficiency and protect those components from aerodynamic heating during the period of ascent through the atmosphere. When assembled together, these major components constitute the complete Scout launch vehicle, ready for its designated mission in space. Let's follow a typical Scout launch trajectory employing the standard four-stage configuration and observe the major events that take place from liftoff to orbital injection. Prior to launch, the vehicle has been erected to a vertical position on the launcher and aligned to the selected launch azimuth. Pitch, roll, and yaw gyros of the guidance system are referenced to this position. Liftoff occurs at time 0, and all subsequent events are timed from this point. Throughout the launch trajectory, the guidance and control systems maintain stabilization in roll and yaw, while a pitch rate program successively alters the pitch angle to accomplish the desired trajectory. Attitude control and stabilization during the first stage burn is accomplished by the movable jet vanes and fin tips on the base A section of the vehicle. First stage burn lasts for 82 seconds, accelerating the vehicle to a velocity over 1,700 meters per second and an altitude of 44 kilometers. First stage burnout is followed by second stage ignition. Separation of the first stage occurs in the B section of the vehicle. Second stage burn lasts for 38 seconds and accelerates the vehicle to a velocity over 3,700 meters per second and an altitude of 89 kilometers. Attitude control for yaw roll stabilization and the pitch rate program during second stage motor burn is maintained by reaction thrust motors in the upper B section of the vehicle. During a brief coast period following motor burn, the heat shield is jettisoned, since the vehicle has now cleared the major part of the Earth's atmosphere. On ignition of the third stage motor, the second stage separates at the C section of the vehicle. Third stage burn lasts for 29 seconds and accelerates the vehicle to over 5,300 meters per second. Attitude control during this motor burn also is accomplished by reaction thrust motors, which are located in the upper C section. After third stage burnout, the vehicle remains in a coast period for the time required by the specific mission trajectory selected. During this period, the attitude control system completes orientation of the stage to the proper orbital injection attitude, and then the fourth stage and payload assembly are spin stabilized. Separation of the third stage occurs at the vehicle D section, followed by fourth stage ignition. The fourth stage burn lasts for 30 seconds, injecting the payload into the programmed orbit. If required by the mission, on completion of the fourth stage burn, the payload assembly may be separated from the motor and D-spin torque applied by the spacecraft to cease rotation. Throughout the entire launch sequence, internal systems of the vehicle conduct all of the guidance, control, stage ignition, separation, telemetry, tracking, and safety functions required in the mission. Fundamental to control of all events in the launch is the guidance system, whose central components are located in the lower D section. Three key components of this system are the Inertial Reference Package, IRP, the intervalometer, and the programmer. The IRP provides the gyro-stabilized inertial reference for attitude stabilization and control, while the intervalometer is the time-based reference for all timed events and pitch program command rates as preset in the programmer for that specific mission. Other major components are the batteries supplying power to the guidance system, the power control relay box that switches the power when and where commanded, the inverter which provides 400 Hertz AC power for guidance components, the roll-yaw compensating unit, the filter box and poppet valve electronics which actuate the reaction control motors, and the rate gyro unit which is located in the C section. Throughout the launch trajectory, the guidance system provides attitude control signals to the first stage hydraulic servo system and the second and third stage reaction control systems. The displacement gyros detect errors from the reference attitude and generate correction signals, which are combined with rate signals from the rate gyros, producing a signal that is amplified and applied to corrective control functions. At times preset in the intervalometer, program changes in vehicle pitch attitude to maintain the planned trajectory are accomplished by torquing the IRP pitch gyro at preset rates and duration. This, in turn, signals changes in the appropriate control systems. Increased trajectory accuracy is achieved by the roll-yaw compensation unit, which compensates for attitude perturbation errors during pitch rate commands that are not sensed by the guidance system roll and yaw gyros. If required by the mission, program changes in yaw attitude also are possible in the same manner by torquing the yaw gyro of the IRP. Components of the guidance system also perform key functions in the ignition of the upper stage rocket motors and other pyrotechnics in the launch sequence. Activation of the vehicle ignition system is one of the pre-launch blockhouse control functions, which include activation of the ignition battery power supply and arming all safe arm relays throughout the vehicle. Arming the relays readies the circuits for application of power to the ignition squibs on command. First stage ignition is initiated on command from the blockhouse by application of blockhouse power to the first stage motor firing squib. At vehicle liftoff, lanyard switches activate latching relays in the power control relay box to enable the ignition circuits for all subsequent timed events in the launch. At the pre-selected times in the sequence, the intervalometer activates ignition command relays in the power control relay box to connect power to the firing squibs in the second stage motor, the heat shield ballistic actuator, the third stage motor, the spin motors and fourth stage motor delay, and the fourth stage separation clamp. At separation, a switch on upper D section initiates a 4-channel timer on the fourth stage module. 3 channels are available for optional payload functions if required. The 4th channel fires the payload separation clamp on the E section, releasing the spacecraft. 3 other active systems important to launch operations are the telemetry, tracking beacon, and destruct systems of the vehicle. 2 telemetry systems provide continuous monitoring of vehicle data throughout the launch trajectory. Major components of the first system are housed in lower D section, with data input instruments located throughout the first 3 stages of the vehicle. This is a 21-channel FM to FM system having a power level of 5 watts, operating in S-band at a frequency of 2230.5 megahertz. 19 of the channels provide continuous data on vehicle guidance and performance, while the remaining 2 channels are pulse amplitude modulated to provide 60 additional sampled data segments covering temperatures, pressures, intervalometer events, and so forth. The second telemetry system is located on the fourth stage module. This is an S-band, 5-watt, 12-channel, FM to FM system operating at a frequency of 2210.5 megahertz. It is operational from liftoff and monitors vehicle fourth stage flight parameters of temperatures, head cap pressure, and accelerations. The tracking beacon, located in the D section, receives interrogation signals from C-band radar tracking stations and responds with a transmitted reply having many times the energy of a reflection signal alone. This unit consists primarily of a super heterodyne receiver and transmitter operating from a single antenna by means of a built-in diplexer. The destruct system provides for either automatic or command destruction of the vehicle, if necessary for unscheduled flight termination. Linear, shaped charge destructors are located on the side of each of the first 3 stages of the vehicle. Safe arm units for these charges are armed by blockhouse control prior to launch. The auto-destruct system contained in the first and second stages provides for vehicle destruction in the event of a structural failure or premature separation of the B or C sections. To prevent auto-destruct at normal stage separation, the head cap pressure switches on each stage open at burnout of that motor. Structural failure or premature separation during first or second stage thrusting would actuate lanyard switches to complete the ignition circuit from internal batteries to the squibs of the destruct charges. Command destruct utilizes a dual command radio link which reacts from coded signals received from the ground station to initiate vehicle destruction. The first command signal transmitted from the ground is an arm signal which closes relay contacts in the relay box. The second command signal, routed through the first relay contacts, closes a second set of relays which complete the circuits from the ignition battery to the destruct charges. The command destruct circuitry contains redundant systems such that either radio receiver and either ignition battery can activate the destruct function. Although the telemetry, tracking, and destruct systems include a ground communication link, all of the internal systems of Scout are independent of ground control. After liftoff, the vehicle successfully completes the launch mission without further external command. Now let's examine in more detail is an aluminum and steel semi-monocoque structure that surrounds the nozzle of the first stage motor. This section is bolted to the base of the motor and provides the main support of the entire vehicle when erected on the launcher. Incorporated in the base A are 4 fixed fins with movable tips which provide aerodynamic control during trajectory through the atmosphere. Mechanically linked to each of the control tips are jet vanes that extend into the motor exhaust plume. These vanes provide the necessary control forces at liftoff when the vehicle velocity is not sufficient for the aerodynamic fin tips to be effective. Base A contains the complete hydraulic system components required to power these control surfaces during flight. Hydraulic control is effected by a conventional servo system whose main components include a battery power supply, hydraulic pump, fluid filter, reservoir, relief valves, and 4 servo actuator assemblies linked to the torque tube connecting vane and tip. The actuators are powered by hydraulic pressure and controlled by the guidance system signals to position the vanes and tips as required for yaw, roll, and pitch control of the vehicle from liftoff through first stage thrusting and coast. The B section is the interstage and separation system between first and second stages and comprises 2 major parts, upper B and lower B assemblies. Lower B is a steel section that fastens to the first stage motor and attaches by a threaded frangible diaphragm to the steel nozzle of the second stage motor. The nozzle structurally supports the upper vehicle stages. The threads of the frangible diaphragm are mated to inner threads of the lower B assembly and threads in the second stage motor nozzle. Separation occurs when ignition of the second stage motor fails the diaphragm, causing release of the threads from the upper stage nozzle. The upper B section is an aluminum and phenolic glass structure which attaches to the second stage motor and encloses the motor nozzle. Contained in this section are 4 44-pound thrust reaction motors for roll control and 4 500-pound thrust reaction motors for pitch-yaw control, plus the hydrogen peroxide system to supply these motors. This reaction control system consists principally of 10 hydrogen peroxide tanks, 2 nitrogen tanks, the 8 reaction motors with control valve assemblies, plus pressure regulators, valves, and fittings to complete the system. The nitrogen system pressurizes the hydrogen peroxide tanks, which contain internal bladders to prevent mixing of the nitrogen and peroxide. On command from the guidance system, individual solenoid valves open and close to admit the pressurized hydrogen peroxide to the reaction control motors. The fuel passes through a catalyst bed in each motor, where it is decomposed into oxygen and steam and ejected through the motor nozzle at high velocity, producing the reactive force required. The reaction thrust motors of the B section control the vehicle through second stage burn and the following coast period when the heat shield is jettisoned. 3 heat shield configurations are available with Scout, the smallest having a payload compartment volume of 0.5 cubic meters, the second 0.68 cubic meters, and the largest 1.01 cubic meters. These heat shields are a phenolic glass laminate and honeycomb composite split shell structure with a metal nose cap. Increased thermal protection of the payload compartment is provided by a cork coating on the forward exterior surface. Inside surface temperature radiating to the payload does not exceed 125 degrees Fahrenheit in a maximum heating trajectory. An internal bumper braces against the fourth stage motor flange to evenly distribute the load. Payload access through the heat shield is provided by either spring-loaded or removable bolt-on doors. The size, type, and location of these are custom installed as required for each payload. The heat shield halves are joined at the separation plane by a series of coil spring modules. Each module contains 4 pairs of counter-wound steel springs that are compressed and latched before installation in one of the heat shield halves. The other heat shield half is fastened to the other side of the spring modules. A metal nose cap completes the heat shield structure. At the base of the heat shield, steel half rings accept a V-band clamp, which, when latched, locks it with a similar ring on the vehicle D section. Inside the heat shield, a drawbar linkage connects the clamp latches and the spring module latches to a dual squib ballistic actuator. On command from the guidance system intervalometer, firing of either squib is sufficient to initiate the actuator, pulling the drawbar linkage. The drawbar motion first releases the latches on the clamp at the base, then simultaneously releases all the latches on the spring modules. The springs impart a separation velocity to the heat shield halves sufficient to clear them from the vehicle. After heat shield separation, the next event is third stage ignition and separation of the second stage at the C section. The C section is an aluminum and phenolic glass structure mating the second and third stages of the vehicle and is composed of upper C and lower C assemblies joined by a frangible diaphragm. Lower C contains instruments for second stage arming, ignition, and telemetry monitoring. Upper C encloses the third stage motor nozzle and houses ignition, destruct, and telemetry systems components, as well as the third stage reaction control system. The threaded diaphragm joining the sections is similar to that used in the B section. Firing of the third stage motor fails the diaphragm, disengaging the threads of the upper section and thus jettisoning the expended second stage rocket motor. During third stage burn and coast, attitude control is maintained by reaction thrust motors located in the upper C section. 10 motors are employed for this purpose: 4 60-pound thrust motors, 4 14-pound thrust motors, and 2 2-pound thrust motors. The nitrogen pressurized hydrogen peroxide system supplying these motors is similar to the second stage system, except only 2 peroxide tanks are required. During the burn phase, the 4 60-pound thrust motors control yaw and pitch attitude, while the 4 14-pound thrust motors stabilize roll. During the coast phase, when less control force is required, the 60-pound motors are shut off, and the 2 2-pound thrust motors are activated to control pitch attitude. Also, a bypass restrictor reduces the thrust of the 14-pound motors to 3 pounds, and these are then used to control both roll and yaw attitude as needed. Note that the nozzles of the 60-pound thrust motors are inclined at a forward angle. After third stage separation, these motors are reactivated and all remaining fuel routed to them as a retro force to increase separation distance before fourth stage firing. In the launch trajectory, fourth stage stabilization and third stage separation are a function of the D section of the vehicle. The D section consists of upper and lower assemblies joined at the separation plane. Lower D itself contains 2 parts joined at the spin bearing. The lower part contains major components of the ignition, guidance, tracking beacon, and telemetry systems. The outer surface is cork-covered, and the inner surface is coated with a gold finish for proper thermal protection of the components. Lower D attaches to the third stage motor and includes an external ring which clamps with the base of the heat shield, as noted previously. A large ball-bearing ring joins the 2 parts of lower D and is the base of rotation for fourth stage stabilization. The upper part contains 4 small solid rocket motors for spin-up forces. In actual use, an internal shear pin prevents rotation until the spin motors are fired. At the separation plane, the lower D assembly contains a series of coil springs with plungers that bear on the adjoining face of the upper D assembly. These springs are held in compression when the 2 assemblies are mated using a segmented V-grooved clamp containing 4 explosive bolts. When the bolts are fired, the clamp is ejected and the springs impart a differential velocity to the 2 stages. As noted previously, in the launch trajectory during third stage coast, the guidance and control system has completed orientation of the vehicle to the proper orbital injection attitude. At this point, the intervalometer commands firing of the spin motors, imparting a maximum spin rate of 180 RPM to the fourth stage and payload, and thus providing gyroscopic stability to this assembly. Simultaneous with spin motor firing, the fourth stage firing signal is initiated, but a time delay circuit defers actual ignition until after third stage separation. Separation occurs on signal from the intervalometer, followed by retrofire of the reaction motors in the third stage, and then fourth stage ignition. The E section, which attaches the payload to the fourth stage, is a magnesium semi-monocoque structure and is available in 4 configurations. Selection is based on payload weight and center of gravity requirements. Payload separation is accomplished in a manner similar to the cold separation of the third stage. The E section assembly, containing coil spring modules, and the payload support ring are joined by a V-band clamp having pyrotechnic devices. On signal from the fourth stage timer, the clamp is ejected and the springs impart the separation force. The payload may remain attached to the fourth stage in orbit or may be separated from it if required by the mission. Although the trajectory shown in this film is a nominal orbital mission, the sequence of events and systems operations are the same for all mission launches. The wide latitude in pitch rate programming, coast period selection, and the many configuration options available give Scout a versatility in performance adaptable to many mission requirements. Scout is designed and engineered as a state-of-the-art vehicle. It is a proven, cost-effective system offering economical capability and a reliability record unequaled by any other launch vehicle. Publications offering more complete detail on Scout systems, components, and capabilities are available from NASA Langley Research Center or Vought Corporation Systems Division.